Welcome to the Study Society podcast, a podcast about university experiences, where we will be discussing topics such as research, academic interests, productivity, and personal interests. Today's guest is Kelly Wurtz, a master's student studying physics, and we'll be talking about how she transitions from film to physics, her research involving Axion Dark Matter, ways to manage mental health alongside academics, and some tips she has for undergraduate students studying physics. Here's our talk. Just one thing before we begin. I do want to mention that I have a stutter, and a little bit of patience goes a long way to enjoying the podcast. Thank you.
Thank you for joining me on my first podcast episode. You're totally like a very helpful person. And I just wanted to ask you, you mentioned that you studied film, and I was curious, what brought you to physics?
Yeah, so I started on my undergrad degree career just as a film student, and I was in high school just sort of interested in film and was sure that I was going to go to college for that. And people always told me, like, stay open to changing your mind, changing your major. And I was like, no, like, I want to do film. I'm just going to do film and be a cinematographer. And so when I started in this film program in my undergrad degree, they sort of gave us our freshman curriculum of like 4 film classes we had to take, and then we could pick a gen ed that we wanted to take outside of that. And I was sort of interested in physics, which I wasn't very great at in high school, but I wanted to try it again because it seemed cool and give it another chance. And so I took the a physics course, which sort of happened to be the first course of the physics major track, just the intro, like classical mechanics, and had a really great professor for that and was really enjoying myself in the physics class. I really liked the dynamics that the students had of working together on these problems, and I really liked the community, and everyone seemed very supportive, and I was having fun. And so the next semester I just took like physics 2, the next course in the track, doing electrodynamics or electricity and magnetism, and also really enjoyed that. I was like, cool, I'm gonna declare a minor in physics. And I did that, and then continued on to like our physics 3 class. And this was sort of while doing the whole like film curriculum, and still thinking like, that's my thing. Physics is really cool. I'm just like gonna take these classes on the side. And took physics 3, which is, we had like waves, optics, and thermodynamics, which were all super fun to me. And I decided I looked at the requirements for a physics major, and I was like, okay, there's 18 or so classes here. I'll just take them. Like, I'll take them alongside this whole film curriculum and come out of college as like a filmmaker who knows physics. Yeah. So what else am I going to do in this like remaining time that I have to fill all these gen eds and stuff? And faced some resistance from my advisors in declaring a major. Generally got the response that it was going to be too hard and I would end up dropping it eventually. So maybe I shouldn't declare it at all. But I was like, well, let me at least like try and fail rather than just not trying at all.
Right.
So I declared the major, and just sort of continued on with those classes, and they started getting more and more demanding sort of side by side as I had to start taking these lab classes in physics and mathematical physics. And then in my film classes, my sophomore year, we had to make like 5 short films in a semester and just be like churning these out. And so that was pretty challenging doing those side by side. But I started noticing on all these film shoots I was on, just mostly with fellow film students, there was the environment of like everyone trying to pretend that they know more than they do, and like people trying to pretend that they're not students and that they've been like doing this for 10 years. And, you know, even though we're all learning, it was sort of like a very egotistical environment. And I kind of didn't like that. I didn't like the environment of being afraid to ask questions or having to pretend that I knew more than I did. And it started not feeling right, not feeling like I could really go on doing this like as a career. I think also the work situation of just like working with like a whole new set of people like every week or like sometimes every day that you're on set, and having to be, you know, God knows where at like 6 a.m. just doing manual labor and lifting heavy things. I was like, this is not the way I want to spend the rest of my life either. And physics just seemed, you know, everything felt very natural in physics. And I sort of got along with everybody in the department. And it really, you know, it's such a supportive community. And those people sort of became my best friends. And just working on these problem sets together with them is such the great like bonding experience. And I especially really liked how people in physics are so willing to admit what they don't know. I think because physics is so hard, it's very humbling. And so nobody's really trying to pretend that they're better at physics than they are, because how do you even do that? You know, like everybody looks at their homework for the first time and is like, I have no idea how to do this. Okay, like let's sit down and figure it out. Yeah. And, you know, even my professors and the more senior physicists that I was around seemed to be very okay with just admitting ignorance and have a more like growth learning oriented mindset. And that I think lined up more with my ideals, and it's just seemed like the place that felt more right for me. But I was sort of like junior year, I've taken some physics classes. I've only ever worked in film, like all my skills are in film. Never done any research. Everybody's taking the GRE and like applying for PhDs. I don't think I can do that because, you know, I haven't even been taking these classes that seriously and I haven't done any research. So I was wondering how I could stay involved in physics. And so I started getting interested in physics education and like going on to maybe get a teaching or like an education degree, a teaching certificate, and a master's program to go on and teach physics. And when I talked to one of my advisors about that, one of the advisors, which was actually supportive and helpful, he brought to my attention basically that I, at any point in my life, can go be a physics teacher and like share that knowledge and get a teaching degree, but I won't really get another chance to get a PhD in physics. That's going to be a lot harder to do like 10 years down the road. And if I want to do research, which I did, I just didn't think I could. If I wanted to do research, like now is sort of the time to do it. And this was midway through my senior year that I was having this conversation with him. And I said, like, you know, really sort of need research experience to get into PhD programs. Like they definitely want to see that. And I'm about to graduate. Like I don't have any. And he just said, so get some. Like you're graduating, but you can still do research. Yeah. And so that was my film. You know, I was becoming like more and more distance from the film world and really devoting a lot more of my time to physics, and got a cool opportunity my senior year to shoot my friend's thesis film. So he wrote and directed it and I was the cinematographer on it. And so that was sort of a fun last experience in film. We spent like a week up in Albany, New York. I went to school in New York City. And so we went upstate for a week to shoot this movie. And so that was a nice, like fun end to my film career in undergrad.
I saw that you did research in your, for the search of Axion Dark Matter. I'm assuming that that eventually led to you having the research that you needed. How did you get there, and what was that experience like?
Yeah,
Was it
so
like a-
when I was faced with this, like, how do I get research experience when I'm graduating, sort of task, I started looking at REUs, which are research experiences for undergrads that are funded by the NSF. So these are sort of like US programs, government funded, to go do research somewhere for a summer. And it's like, cool, that sounds perfect. Sounds like a great way to get my foot in the door. And so I applied to a bunch of these REUs, and one was at University of Colorado, Boulder. I started getting interested in photonics and like electrical engineering a bit, and optics. Just I liked cameras, so I was like, how can I sort of bring that into physics? And I program at the University of Colorado Boulder got back to me, and they were like, you're not eligible for this program because you're not an undergrad. Like, you don't qualify for this funding because you'll have already graduated, but we want to accept you. So like, I was like, can you just hire me for 3 months and like do something like that? And they told me basically that they would make sort of a short-term, like, summer job for me doing the same research project. And I was totally stoked about that. And like, I was still in New York, but signed a lease in Boulder, made all my plans to move out there. And then basically found out that that job had fallen through. Like, they no longer wanted to hire me. And tried contacting the professor who I was going to work for and asking, can we talk about this? And she hung up on me. So
oh, wow.
I had these plans to move to Boulder, but my initial plans to do research had totally fallen through. And so that was a big leap that I've taken in my life, to still move to Boulder and kind of trust that something would work out, even though I didn't know what it would be. Because I still, I had my lease signed there. So I was like, I'm going to move here and just start talking to people and see if I can pull anything together. Yeah. And I think as I was sort of transitioning from moving to New York to Boulder, I emailed maybe 25 professors just asking, like, sort of telling them about myself and that I'm looking for experience. Can't remember if I was trying to get paid or not. Probably just get hired at that point. Yeah. Maybe 8 got back to me saying, sorry, no. And the rest just didn't reply. Mm-hmm. And so that didn't work for me. Couldn't get any research positions that way. But I was, via this project that fell through, I was sort of in contact with another person who worked at Boulder doing science education, because that had sort of come up as another job opportunity for me. There's this nonprofit at Boulder which does interactive simulations for teaching science and math, and they were looking for somebody to come make animations and make videos for them to provide resources to the teachers that use these simulations, of just how to use them and like featuring new simulations and stuff like that. And so when I first moved to Boulder, I basically started doing that. I was in the science education sphere, not necessarily doing anything directly with science education, but using these motion graphics skills that I had gotten in film school to help this nonprofit. And I was in the physics department, and so talking to people who worked in the physics department, and a lot of people I worked with either went to school there or had gone to school there, some for physics education and some just for physics. And through some people I worked with at that science education nonprofit, I got into contact with someone who I could do research, basically, because I was pretty open about the fact that that was my goal. I was trying to go into research somewhere, and took a tour of someone's lab, and one of the projects that he was working on was axion detection. And I had learned about these hypothetical particles called axions in one of my had an undergrad like reading about particle physics class, and had learned that the axions are this a hypothetical particle and candidate for dark matter. And he was working on a detection project for them, and also working on some quantum computing stuff. At the time, I wasn't so interested in that, but I was like, cool, particle physics, this sounds awesome. Like, I'm going to get started on this experiment. And so that was basically how I ended up in that lab.
Wow. That's super cool. Like it seemed kind of like a natural, like maybe like a film student's journey. Like, I'm gonna move here, and like things are gonna work out, and I'm just gonna have faith, and it actually did, which is great. So, what did you do in terms of being a part of this research project in search for Axion Dark Matter?
So when I first started research, I guess the most intimidating part of research for me was like, the sort of heart of research is being on, the cutting edge of things that like nobody knows about physics. And I'm like, little me, like I just have this undergrad degree where I like sort of know these things I learned in undergrad. Like, how could I possibly contribute to questions that like nobody knows the answer to yet? And so I knew nothing going in. And in this lab, you had to know a lot about electrical engineering and quantum mechanics, and actually not so much about particle physics. I did the least directly like with particle physics. That's just what lured me in. But I started learning about mostly about electromagnetic cavities, which are it'll be like a block of aluminum with some empty cavity in the middle of it, in which electromagnetic waves can bounce around. And the frequency of the cavity is just sort of determined by the size of that hole in it, how many or how long the wavelength is that can resonate in there everywhere.
So what did you learn about Axion Dark Matter through your research project?
Yeah, so I learned that Axion Dark Matter is this candidate for dark matter, which is this pervasive source of mass in our universe that we have no idea what it is or what it's made of. It's very likely some foreign substance or some particle that we haven't detected yet. Or it could be other things. It could be black holes in some way. I don't really know much about that, but there's lots of different candidates for dark matter. But axions are one of the leading ones. And this was a particle that was hypothesized in the 70s to actually solve a different problem in theoretical physics called the strong CP problem. And I won't get too much into that, but in trying to solve this problem, they had to basically introduce a new particle to the standard model. And this particle, the properties of it that they looked at made it look very consistent with dark matter in our universe. And so it quickly became a candidate for dark matter. But one of the things about it is that nobody knew its mass. Mass is one of these things that isn't predicted by the standard model. It's just one of these parameters that with our current theories, we just have to measure. There's no way to sort of extract it. And so since we don't know what mass it's at, by just the quantum mechanical relationship, E equals h bar omega, omega being the frequency of some particle, and E being like the energy or equivalently in particle physics the mass of something. This gives us a relationship between the mass of an axion and the frequency of the particle. And since this is a very light particle that occurs just in massive amounts, it's almost like some collection of photons, and how we don't really think of them. It's not smartest to think of them as photons. It's smartest and most helpful to think of them as a wave. And axions would kind of be the same thing. So if the axion hypothesis is true, there's basically these waves of axions throughout our galaxy and every galaxy. And so we are trying to pick up on this signal, like an FM radio, how you turn your radio to a certain frequency to pick up on the signal that's just out there. That's exactly what we would have to do with axions. We just don't know what frequency we'd have to turn a radio to. And so you have to not only create something that can detect this frequency, but create a detector that's tunable over very, very, very wide frequency ranges, because it's only constrained within like 34 orders of magnitude, which is just unbelievably enormous. Way too many frequencies to search with like the technology we currently have. And what makes it hard is not just the amount of frequencies we have to search, but also that the signal is so weak. So even at any one given frequency, it's very hard to detect. And so in any experiment you have, or at least any experiments you're trying to do, detect a signal, you would have the signal, and then you'd have some noise, some random fluctuations that are interfering with your ability to gather information about the signal. And the minimum amount of noise you can have in any experiment really is the noise of vacuum. You can get rid of thermal noise by cooling our experiment down to superconducting temperatures. We know how to do that. We can do that easily. But even if something is superconducting, it's not going to get rid of these fluctuations that just come from the inherent uncertainty of the vacuum. And you can sort of most easily think of vacuum fluctuations as just, in quantum mechanics, we can't really measure the energy of something to be exactly zero. And so these fluctuations in the vacuum are a manifestation just of the uncertainty principle. And there's always these sort of like bubbles of energy going on. And that's sort of generating noise in the same circuits in our experiment that we want to detect an axion with. And so that is the main source of noise. And if you're thinking those must be very small, so it's probably not that bad, you're right in thinking that they're very small, but the signal we're trying to detect is actually 1,000 times weaker than the fluctuations we get from vacuum. And this is the unavoidable noise of the universe. We can't make our experiment any colder to get rid of these vacuum fluctuations, and yet we're trying to detect this signal that's buried very far beneath all these. And I like to think of the image of Princess and the Pea, and these vacuum fluctuations are just 1,000 mattresses, and this Axion Dark Matter signal is the P that we're trying to make very precise measurements to measure under all those mattresses.
Oh. That's like a super good analogy.
Yeah.
Like I can picture it.
Right. And there's just, trillions and trillions of these mattresses we have to search. And so how we actually detect this signal is by taking an electromagnetic cavity, which is just a block of aluminum with a hole carved out in the middle of it. And the size of this cavity in the center of the block corresponds with the resonant frequency of the cavity, or which wavelength of electromagnetic waves can resonate in it. And if the frequency of this cavity is the same frequency as the axion signal, and we place it inside a big, very strong magnetic field, then the magnetic field would cause the axions to convert to photons. And within the cavity, the waves bounce around a lot before they decay out. And so basically you can sort of generate a signal of these photons that are being generated by the Axion field and build them up together into something that we can actually detect. But the cavity has to be the right resonance frequency. And so we have to make the cavity itself tunable, sort of adjust its geometry in a way such that we can scan through frequencies. So since it would take us so long, if we knew what frequency the Axion was at, if we knew which mattress the P was under, we have the technology to measure it. We could just tune our thing to that frequency. And if we wait, a few hours of just integrating power, then the signal would start to emerge from the noise. But we have to actually cover frequency ranges over some time. And so we want to increase really the rate at which we can scan through frequencies. And so I think the most important Axion research going on right now is not that which is just sort of doing its, process of stepping through frequencies, because it's just like buying lottery tickets in hopes that you win the lottery. It's probably not going to happen. But if you are able to do some R&D and make a new apparatus that can sift through or buy thousands of lottery tickets at once and go through them much faster, then you actually have hope in the future of like finding the Axion. This is where I like to think of like the golden ticket in Willy Wonka and the Chocolate Factory. Like the faster we can go through these boxes, the higher the probability that we're going to find the golden ticket in one of them. And so my project in Boulder was basically doing some R&D for these Axion searches to increase that scan rate. And how we do that is actually, it's a concept called quantum squeezing, where these electromagnetic waves in the cavity, they can sort of be split up into these two possible observables that are sort of like every wave can be broken up into its cosine-like and sine-like components. And these are called like the X and Y quadratures. They're basically two variables that like the wave is described by. And the uncertainty principle gives us this relation where we can't know both of them. We can't measure both of them to arbitrary precision at the same time. They obey the same uncertainty relations as like position and momentum. But it only puts a limit on multiplying the uncertainties together. They have some minimum value. It doesn't say for any one of the values, it doesn't set any minimum on that. It just says if we measure one very precisely, we have a very large uncertainty of the other one. But that can actually help us, because if we prepare the cavity in a state where we can actually squeeze the variance, basically, there's variance in these X and Y quadratures, and we can squeeze the uncertainty into one of the quadratures, but the Axion signal would be manifesting in both, but we've lowered our noise in one of the quadratures, and therefore we can enhance like the signal to noise ratio that we get if we just make a measurement upon that squeezed quadrature. And so in doing that, manipulating these states of light in quantum ways, we can increase the signal to noise ratio of this very weak signal over what we'd be able to get classically. And so that was sort of the experiment that was going on when I first joined the group in Boulder. And my project then was sort of to improve on that even further and use entanglement actually as a way to even further amplify the signal to noise ratio and increase the scan rate.
Wow, but that's extremely fascinating. And I just feel like maybe it's like natural to ask you then, how did entanglement then play a role in your research?
Mm-hmm. Yeah, so that's something I thought was super interesting at first, because entanglement is a very mysterious thing, and I was super confused how it can actually improve a search for dark matter. But this concept with entanglement, how it works is you have now two cavities. You have this cavity that detects axions, and then you just have a second sort of auxiliary cavity that's connected to it. And you can pump photons into a part of the circuit between the cavities, and you do that at the sum of the two cavity frequencies. So what happens is the photons go in and they split in two, one at the frequency of one of the cavities and one at the frequency of the other ones. But since they both came from the same parent photon, they're entangled. And so you get these two cavity states, which are entangled with each other. And this creates what's called a two-mode squeeze state. So instead of just one cavity state where we've pushed sort of the uncertainty into one of the quadratures, we now have a how do I say this? We now have squeezing between the two cavities, which is kind of a hard thing to understand and visualize because neither of the states in either of the cavities are squeezed. But if I were to take one quadrature, say one cavity, and one quadrature of the other cavity and plot those together, I would see a squeeze state. And so what that basically means is that there's correlations between these observables in both of the cavities together as a two-mode system. They form a squeeze state. And whereas in this squeezing procedure that I described before, where we're just squeezing a single mode, we're trying to lower the noise and then measure along that quadrature in which we've lowered the noise. But when we make a two-mode squeeze state, we sort of use the inverse principle where we're squeezing or we're decreasing the variance in one set of quadratures. That means we're increasing it in the other ones. And since we're doing that inside the cavity, the ones that we increase are amplifying the axion signal. And so instead of using this as a method to decrease noise, we use it as a method to amplify the axion signal before it exits the cavity and is polluted by this noise that's outside the cavity. And so we now have these sort of complementary ways of improving the axion search. One where we can decrease the noise by squeezing, which works sort of outside the cavity. And now one where we can use squeezing to amplify the axion inside the cavity before it gets polluted by this noise outside. And so my project was just to work out the theory of this entanglement experiment and how that would work. We didn't know if it would work. So I made these simulations, did analytics, learned about how people think about microwave engineering and quantum optics and how I could model this system and how we could figure out if it works. And most importantly, what kind of scan rate enhancement we would get from this protocol. If this basically ends up widening the range of frequencies over which our detector will be axion sensitive. So if we're amplifying the axion signal, then we could see it farther away from like the cavity resonance. And so when we have a wider bandwidth of sensitivity to the axion, we can then take bigger steps as we step through frequency space, and that will increase our scan rate. And we found through these simulations that just the entanglement procedure alone can make up to a 20 times faster scan rate, which is pretty huge for like searching through these big frequency ranges. And so over the past year or so, we've been writing a paper on the theory work we did behind designing this experiment and showing how it will work, that we've thought through all the possible factors that could come up that would like affect it, and how we would build an experiment in which it does work. And then some more people came onto the project as I was leaving last year to actually make a test bed run of it and make a little fake axion, a test experiment in Boulder to see if this would actually work in the way we think it would. And that's sort of starting its initial stages now of beginning a test.
Oh, like I was just kind of curious what kind of reactions people gave you upon you presenting your research. I think you told me earlier you presented this exact research at Aspen, Aspen Center for Physics.
Mm-hmm. And I was also able to give a talk on it at the APS April meeting, which happened virtually last year, just as we were sort of getting started writing the paper. And it's had a pretty positive reaction because a lot of scan rate enhancement R&D research in the past, or at least this squeezing idea that was worked out a few years ago, the sort of first squeezing, first way that squeezing has benefited Axion searches gave us like double or like triple times the scan rate enhancement. And that's awesome because you're cutting, 10,000 years it might take to find it into 5,000 years. But we really need to like go beyond that if we want to, search these frequency ranges in the next, lifetime maybe. And so increasing our scan rate by a factor of 20 is huge. It's a lot, it's actually a big step in getting towards a place where we have the technology to search this. And more than that, it's still maybe at 500 years it would take us to search this. But with this development, along with these squeezing things that we've developed in the past, alongside future things that we could use to increase scan rate enhancement, those will eventually come to build on each other. And we can use these together in a way that we can actually search the possible values for the Axion frequency. And so people, I found people were pretty interested in it, but most of the talking about it I did was early last year. And that was before we thought through a lot of the, a lot more just sort of technical problems that we come up that we still weren't exactly sure it would work. And so we spent a lot of last year just really making our simulations and our models of this more robust and accounting for everything we possibly could and making sure that with all these different factors coming in, we could still achieve that scan rate enhancement. And so our paper on it is nearing its end and should be, I think, completed within the next few weeks. And so that's an exciting point to get to, of actually having worked through all this stuff and be submitting this for publication.
Wow. Congratulations, by the way. Yeah, I'm sure it's a really big step to do research and then publish work. Mm-hmm. Sorry, I have to ask you, what when you made simulations that involved programming simulations and there was a lot of computer work, basically. Mm-hmm. Wow. How long did it take you to be able to code simulations coming from film to physics?
Yeah, so I guess my coding knowledge going into this project, most people will learn Python in undergrad. And so I had used it in just to the extent that I had to use it for my lab courses. And we learned some things in class. I audited a class at Boulder sort of about Python stuff. And so a very, very weak working knowledge of it. And then when I got into my lab, I found out that everybody used MATLAB anyways. So I started to learn MATLAB too. A lot of our data acquisition code was written in MATLAB. But my simulations actually I started doing in Mathematica. And it just started out very, very simple. I didn't really get the task of make a simulation. It was sort of because it's research. We don't know what we're doing, even my advisor, we figure out as we're going, what the problems are, how we're actually going to do it. And you only really figure out how to do it when you run into those problems. And so I learned theory, which is a way in microwave network engineering of just sort of saying, if I send a signal in, what comes out? If I have these resonance structures and I have these decay rates, and you can sort of model the system very basically by that. And there's a lot of analytics to be done there. But then when you sort of make that theory and see what it says, you think, okay, well, what's the next level of complexity? Like, what haven't we accounted for that we can now add in? And so those simulations just started growing more and more complex. And I guess I will say this is still all in Mathematica, and Mathematica can do a lot. I've always sort of conflicted on whether to call it coding, because you can do for loops in Mathematica, you can do simulations, but it's also like too pretty of an interface, it seems like, to be called coding. You can like make these really aesthetic notebooks and actually see your like equations written out, and they look like equations in front of you. And so I don't know if I can call it coding exactly, but it has a lot of the same functionality, and I like working in it because it's very like pretty, and you can actually type Greek letters and fractions and stuff like that in like ways that look nice. And so I just ended up, by the end of this project and us adding more and more levels of complexity to this, just this massive Mathematica notebook of everything we had sort of accounted for. And when we figure out how to predict the scan rate enhancement at one frequency, well, then it's like, okay, well, how does the scan rate enhancement change as I tune my cavity around? And will I get the same scan rate enhancement if my two cavities are a gigahertz apart in frequency versus a megahertz? You have to think through all these things and come up with a prediction for the scan rate enhancement that we are confident in, and we know we've thought through everything, and that we can ethically put forth and say, we've thought through everything we possibly can, and like, this is the scan rate enhancement this will achieve. And so all the simulations that I did for the actual project, I call my project Ceasefire, and that stands for the Cavity Entanglement and Swapping Experiment for Improved Readout Efficiency.
Wow, nice.
You gotta make an acronym for it.
Yeah.
So all my Ceasefire simulations were done in Mathematica. So I think Mathematica has a reputation for being liked by theorists and not by experimentalists. But as a theorist, I'm just gonna say I love Mathematica, and don't be afraid to do simulations and coding in it, because even the interface might make things a lot easier of being able to lay things out in like a more organized pattern in front of you, and its functionality is really great. And even doing analytics and stuff and my problem sets in undergrad, I wish I had known how to use Mathematica, because if you're trying to take the derivative of a long expression, Mathematica can just do it for you and make sure there's no mistakes, instead of you doing it by hand and missing a minus sign or whatever. Like, it really is a good tool to have in 21st century physics for just like doing math. It's like a math helper. So I would definitely recommend, people know how to use Mathematica, but also people know how to use Python and or MATLAB are like great places to start for for any projects that really might need them. If you're doing computational physics, data analysis, you're not going to be doing it in Mathematica. You're going to have a more like a programming coding sort of based project would require those. And knowing those is a great place to start. But actually, some like things that I've had used very, very little in my career.
Yeah. I guess just for just so that I could I would understand, I basically pictured Mathematica a little like Jupyter Notebook, right? Or okay, yeah. Because I have never worked with Mathematica, but I just assumed it sounded like kind of like a combination of like LaTeX and Jupyter Notebook in some way. I don't know what Jupyter Notebook's capable of in symbols. Yeah.
Yeah, Jupyter Notebook is just breaking up Python into chunks, and sort of it can use these same cells in Mathematica where you evaluate one at a time, and definitely keep things a lot like prettier and more organized. But then Mathematica is nice because your fractions aren't just like 3/4. You can actually write like something that looks like a fraction, and you can write subscripts and Greek letters and stuff like that. Yeah. And so that's very pleasant to work with, but also a big fan of Jupyter Notebook when I have to use Python.
Yeah. Cool. So moving on, you mentioned how Aspen Center Physics is sort of like physics heaven. Could you explain? I mean, could you maybe tell a little bit about about what your experience at Aspen Center of Physics was like for you?
Yeah, so I had found out about this small conference there from my advisor, who's actually helped organizing it, a conference for quantum information for fundamental physics. And the Axion project fell under that because quantum measurement is really a study of quantum information. You know, it's how much information we can gain from a system that's limited by these things like the uncertainty principle and what kind of measurements we're able to do and things like that. And so me and the other people working on my project went to this conference to, I was presenting a poster, one of my lab mates was presenting a poster, and then just a lot of other people doing Axion research in different ways were giving talks there, presenting their work there. And there was also people talking about different fundamental physics, talking about tests for quantum gravity, how we might test that, or, you know, even how we're studying black holes with quantum information. And this whole, I started getting really, really interested in all of these different ways to apply quantum information to physics. And the actual center for itself is, you know, it's in Aspen, Colorado, which is this gorgeous, gorgeous place that people really go for, like skiing and snowboarding mostly. And this they have this very, very cute, peaceful little physics center, just middle of winter. So it's surrounded by snow, and getting together there with people from my institution, as well as all these other people that care about quantum information for fundamental physics, was just so nice. And the center itself is like beautiful and was a really wonderful place to hear about physics and talk about physics for a week. And I'm assuming they do this with all conferences there because it's Aspen, but how they schedule it is there, you listen to talks in the morning from like 9 to 12, and you listen to talks in the evening from like 5 to 7. So what do you do between then? Everybody obviously goes and skis, like
Wow.
goes out and snowboards. I think they schedule it for that purpose because, you know, as lovely as physics is, it's even better to go on like a physics vacation and go and ski and snowboard at the same time.
Yeah.
And so, yeah, people would just come back in the evening, you know, with their like snow boots on, like just having come back from the mountain. And so it really feels like a physics vacation because, you know, you're hearing just about the coolest stuff and also in the most beautiful place with awesome people. And yeah, that was a lot of fun.
Can you ski?
I can. I actually did it on that trip because skiing is like a really expensive thing in Colorado, and people will get these like year-long passes that actually allow them to go every weekend. I didn't have one of those, and I'm always afraid I'm gonna like break a knee or something when I go skiing. Yeah. So I just stayed back at like the Center for Physics in the afternoons, and so peaceful. It was so peaceful there. Then everybody goes out to ski, and I could just work there. They actually give everybody like they have like 30 or so offices there, and the conference was only maybe 50 people, so you just sort of claim an office with someone and get to have a little room to work in for the week.
Cool.
And yeah, I still kept doing like some research there. Theory research is great because you can do it anywhere.
Yeah, well, it sounds like a lot of fun and a great way to just meet other physics students and researchers, and I'm sure you've maybe built some bonds with some people that you still talk to today, maybe.
Yeah, I got to it's always fun meeting like the wider Axion detection community. You're like, oh cool, you're like one of 50 people in the US that, you know, spend all their time looking for axions with cavities. Like, let's talk about it. We do the same things all day. And, you know, yeah, these people from all over, you sort of, I didn't really believe that like physics could feel like a small community at first, but you actually do sort of, yeah, just start hearing about the same people and seeing someone on a paper like, oh yeah, I met them there. And it's cool to, yeah, just feel a part of like that wider community. And I also got very interested in this black hole research that people were talking about there, and applying quantum information to that, and sort of hearing people talking about that and talking with people about that was a really good opportunity to see what different pathways I could take with that.
So what are your goals long term with physics then, and your academic career? What do you plan to do further research in?
So right now I am in a master's program that is happening remotely, which is not ideal, but you can actually, theory research goes on as usual, even if it happens over Zoom. And I'm doing research in black hole thermodynamics right now for my master's essay. Also sort of working on a side project that came up in my program on a more strict quantum information, quantum measurement theory problem. And I want to lead into applying quantum information science to black holes. And this all came up, a few decades ago when we sort of came to the realization that information can be studied physically, that's the most fascinating thing to me, is that it's this very sort of seemingly conceptual thing, but we actually realized that when you learn about the relationship between entropy and information, they're nearly the same thing. And we already know entropy is a very well-defined physical quantity. And so we started looking at, entropy in black holes. That became a really significant problem because the very, very well-respected second law of thermodynamics which says that entropy always has to increase on average in a system. It seemed like when we took a system with a bunch of entropy and chucked it into a black hole, which as far as we know only had one microstate only possible. It was just described, by mass, charge, spin. It's a very it's a black hole. There's no different configurations of it. It seemed like all that entropy just disappeared, it went from big box of gas with trillions of different possible configurations into this black hole. It's just one possible configuration. So where did all that entropy go? And since we respect the second law of thermodynamics a lot, it seemed like this was a really big problem. There was loss of entropy and therefore loss of information in the universe. And some people, intelligently weren't ready to accept that. And then Stephen Hawking discovered this phenomenon of Hawking radiation. And this has led sort of to a few decades of research on just what the heck happens to information in black holes, because it's been so illuminating into what happens to black holes. And we're still in the dark about that, of course, but applying this concept of information to black holes has given us a new lens with which to study them, which I think is important in sort of a time when not a lot of, we've known quantum gravity is a problem for almost 100 years and we haven't been able to solve it. So sort of having a new angle to look at that with, or a new lens, seems very promising, especially one where, we haven't considered this aspect of it at all. What could that tell us? And what could that tell us about the life cycle of black holes, but also could it point us towards a theory of quantum gravity? And what could it tell us about the features of that theory? I'm very interested in, continuing sort of this investigation into more fundamental physics with quantum information. And people are also looking at cosmological questions with quantum information, which I know less about, but the life and formation of the universe, emergent space-time and things like that can be addressed from an information theoretic perspective. And that's just so cool to me. So I would love to go forth in that type of research. My next goal is to do a PhD program in that after I finish my master's. And I'm sticking with the naive plan of I want to do academia for now. I think a lot of people already even in undergrad, people already sort of plan on selling out after their PhD, because it is really, there's only however many professorships or just however many physics professors die in a given year. And so they don't like open up very often. Even postdocs are very hard to get. But once again, I'm of the mindset that I'm going to try and fail before I just decide to fail.
Right.
And, see if it's possible. And I really want to go forth in my PhD with black hole research and go as far as I can in academia and see if maybe I get interested in something else along the way. But as of right now, I would just love spending my entire life thinking about physics. It sounds ideal.
Yeah. Wow. That's like your interest for quantum physics is like definitely inspiring, and I hope you do see the end of your PhD journey and to go on and like do all that
Thank you.
All that research. I was wondering, what does a productive day look like for you now?
Yeah, so there's a lot of, in my current program, days are very different, there is always a couple hours of like meetings a week. I still have meetings for the Axion project with Boulder people. I meet with my advisor for master's research, and then somehow just like more meetings start popping up all over the place. And there's also a lot of virtual talks. Like one of my favorite things about the pandemic is that if a talk is happening like on the other side of the world or at like a conference that I never would have gotten to beforehand, I can just watch it, I can drop in. Most of these things aren't private because most physicists don't like being like gatekeepers of knowledge. If it's online, they're just going to make it public. And we've also at my institute had speakers that I think we wouldn't have been able to get otherwise. Like we got to listen to Roger Penrose do his first Zoom talk a few weeks ago. And I don't think I would have gotten to hear him talk or like hear about this stuff if it weren't just for being able to hear things virtually. So I love, attending a lot of talks. Talks are a great way too to just hear about things outside your field, things that you might be into, and you'll probably only understand like the first third of them. Get like the good intro before they get to the expert stuff. But even that, has just been really cool in hearing what's out there. And then currently I'm finishing up a course in quantum information, which is more like a quantum computing class, actually. So I'm learning about quantum algorithms and how quantum computing is can be more efficient than classical computing. I'm still working on finishing up the Axion paper and doing this black hole research. So I'm going to spend the rest of the day in Mathematica probably. And as for productivity, I don't want to pretend like I'm the model for productivity. All my days start off at 6 a.m. and I'm super focused all the time because I've had to learn how to be more like gentle with myself and my expectations for myself throughout the pandemic, because we can't pretend this is like a normal time, where we've learned all these skills to keep up with productivity throughout our life that sort of like going out to coffee shops that like a lot of people don't have a chance to do. And I think we do need to be not as hard on ourselves throughout all this, or just not as hard on ourselves as we're, going through any events in life that make it harder to do physics. But in general, I find to stay productive, having a to-do list, I definitely, like to make lists and just like see everything I have to do in front of me. I really like breaking things up into steps so I can not only check something off like at the end of a few days when I'm done with some problem set, but, check things off when I'm done with each individual problem. Helps me feel like I'm making progress and keep me motivated. I guess the one like big thing I do outside of physics is weightlifting, which I've been able to get back into just recently because gym's just reopened. But I find that like starting the day with exercise, at least I'm like a morning exercise kind of person, but starting the day with exercise really starts it on a good note and, already accomplished something by like 8 or 9 in the morning, feeling good from those endorphins and just sort of like ready. You're much more awake and like ready to take on whatever tasks.
Yeah.
And honestly, I have a sort of a hard time sometimes with the initial hurdle, you know, like getting started on a problem set, your brain's like, it's going to be so hard. Like, you're not going to know how to do it. You know, it's hard to just jump into the problem. And so for productivity, I've been really trying to just get better at just getting started on things, you know, because once you're in there, you find it's actually kind of fun, but we always like build things up in my head to be so much harder than they actually are. And so really just cutting back on distractions and jumping into things to like as soon as possible to get started on them and have them sort of going around in my brain. I did just download like one of those Chrome extensions that blocks websites for you.
So, okay. Was it like strict? Like I might have it right. Like I got one too. Like I got one called strict workflow or stay focused. Yeah. Like I'm very sorry.
Yeah, I think I use stay focused.
Yeah. Like I find it helpful too.
Stay focused is good because it gives you sort of like motivational messages to keep working when you visit one of those websites. And then I have the option checked when if you want to change any of the settings, you have to type in like some really long like paragraph on like just how bad procrastination is.
Wow, that's cool.
Yeah. Like that will probably keep me from changing any of these settings. I have to like apply it to my other browsers somehow too, though, so I don't go like check Instagram on Safari or something.
Well, like I don't do lists because like I'm not really good at planning, and it's one of my 2021 resolutions to plan better. Like I can't say I'm a productivity expert in any sense either, and in fact I think I'm a terrible student, but I like how simple a to-do list sounds. Yeah. And simple is great.
It's great to have a Google Calendar to just plan my day. Like sometimes if your to-do list seems really long, it's like, oh God, like how will I possibly ever get through all this? But then if you write like, this will probably take 2 hours, this will take 30 minutes, you know, this, I might want to spend 4 hours on this problem set. And then you just put that all in your calendar. It's like, oh, I could finish this in 2 days actually, if I just stick to this schedule. And you can see, you know, I just need a calendar to sort of have things planned out, and you can see how different tasks will like fit into your other events that you have to do throughout the day. And I find that like helpful to have that visual.
Yeah. I feel like this part of the conversation is just important. Like how important is mental health in academia, and what do you do to stay mentally healthy? Yeah,
I think mental health is just important for like life and being a human in general. But in academia, we're doing very like challenging tasks, learning a lot of like new things every day. It's really easy to compare yourself to people, and it's really easy to overwork or like see other people who are overworking. And I think this past year I've been taking like a closer look at my mental health, thinking about sustainability and like how can I love physics, but if I'm like constantly stressed out on a day-to-day basis, you know, it's not just gonna like end. Like I need to find some way to enjoy physics on a day-to-day basis if this is what I see myself doing for like a long time in my life. And I've talked with, I think one thing that everyone I've talked to in physics seems to agree upon is that like their emotions and sometimes sense of self-worth depend on like how their research is going. So it's just so easy to fall into that, because when, you know, you messed up on something in your research or like it's not working, you know, you just feel like a bad physicist. You feel like you can't get it right. And then when things are great, it's like, wow, I'm the best person in the world. Like I'm a great physicist. My advisor's happy with what I did. Like, wow, this is the best day ever. And while those highs are super great, you know, your worth is the same throughout the whole thing, and should not. Research it has, you know, it will be bad sometimes, it will be good sometimes, it will be bad sometimes. And so if you like latch on your happiness to that, you're like latching your happiness onto a roller coaster that's going to be down sometimes and going to be up sometimes. And it is hard to stay productive or like find motivation in those times where you don't feel like a good physicist, because, you know, you think, you know, even if I try my best, you know, it's you know, still going to be bad. And how can you motivate yourself when you're having those thoughts about like your abilities? And so I at least have been trying to define other measures of success for myself. For example, like at the end of the day, I ask myself if I tried, because sometimes even that's, you know, I'll be really scared of a problem set and be telling myself I can't do it, but did I try? You know, if I tried for the whole day, I can't really be that, you know, what else could I have done? I can't really be that upset with myself. Or especially if I'm having trouble, did I ask for help? You know, did I try? Did I ask for help? That's much more fixated on things that you can control. And I think if you try and you ask for help, you'll get a lot farther than, you know, if you go into a problem set thinking like, I have to do this perfectly. And yeah, another thing is on the topic of perfectionism. I think, you know, a lot of people just in general have this idea that, you know, if I'm making a presentation, I want it to be perfect. I want to, you know, have all these grand ideas for something, the problem set, I want to have no mistakes on it. I want to get 100 on the test. When really I've heard perfectionism is procrastination. And it is true, because you're sort of delaying being able to do more by just doing like fewer things perfectly. And I also really like the quote, "Dare to be average," because it takes a lot of courage to go into some topic, some field, some project, like knowing that it might not be awesome. It's really easy to commit to something if you're already really good at it. You know that it's going to turn out well, like it's super in your comfort zone. But it's a lot harder to commit to something when you don't know what you're doing, and you probably won't get it perfect and you will make mistakes. Like that's really hard. And the most courageous thing you can do sometimes is just be okay with doing an okay job. And I think that it's just amazing how much more ground you can cover and how many more things you can learn and experience you can get by just not being a perfectionist. And that definitely improves, I think, your mood too, when you're not expecting perfection from yourself. That's sort of, a dumb thing to expect anyways, because you're not going to achieve it either way.
Uh-huh.
So trying to tackle perfectionism, planning helps a lot. You know, exercise helps with my mental health. And something that's new this year to me is, I think, just not blaming any mental health struggles on myself, because sometimes when you're, you know, depressed and feeling a lack of motivation, it's really easy to address that with like, I'm not being disciplined enough, or like, I usually feel motivated. I must just be like being really lazy right now if I'm not motivated. When they're actually, you know, depression is a chemical thing that happens in your brain. And there are studies that show that when you're depressed, like it's harder to do things. You're more tired, like you need more sleep. It just leads to a lack of motivation. And so it feels like you're being lazy, but it's actually just, you know, things happening in your brain that's making it harder to do everything in your life. And it's not your fault at all. And so I've been trying to be a lot more just like patient with myself. And when I feel depressed, like instead of thinking, how can I fix this? Just being like, okay, maybe I need to take it easier for like a day and decrease my expectations of myself, because there's this stuff going on in my brain that's making it harder to do everything. And so I can't really expect the same output of work as I do when I'm like feeling awesome.
Yeah.
Also being honest with like my professors about mental health struggles. I've done a lot of I know, like, I think a lot of people who struggle with anxiety and depression have made up lies to their professor. Like, okay, well, anxiety isn't a valid excuse. So, I'm going to say I'm feeling like sick. I'm going to say I have the flu, because that's a valid excuse. You know, mental health isn't. And if we're trying to work towards a society in which, you know, we obviously know just through our own experiences that mental health can be debilitating. And like, sometimes you, might feel too anxious to go to class or something. And so we know through our own experience that these things can affect us in the same way as like a physical illness. And I think to allow that to be treated in the same way and sort of decrease this stigma around it, we have to be more honest with people around us. Like if we're going through something, not lying about it, and sort of having the courage to say like, hey, I'm really, just feeling a little down today, or I'm feeling really anxious today. I'll get back to you on that tomorrow. And we just need to be more open about the conversation about it. And it's been very sort of liberating to just not put that stigma on myself and, at least not be doing that to myself, and just being, honest with people, being patient with myself and more gentle with myself. Yeah. Just at least, you're already feeling the like pain and pressure of mental illness, and then you make it worse by like blaming it on yourself, or like telling yourself that it's a bad thing or a reflection of your worth or something. And so you can sort of get rid of that second level of it by just sort of general acceptance. And I think everybody's different in what they can do to sustain their mental health. Like talk therapy works for a lot of people, but some people it doesn't. And I know exercise helps for most people. Medication helps for some people. And it's just sort of no recipe is going to help everyone. And so you sort of have to just see what makes you feel good and be like brutally honest with yourself about what sort of works for you and helps you be at a place where you're enjoying your work on a day-to-day. I find writing helps a lot too, sort of getting in front of you, analyzing your day. You can analyze it like a scientist, like write down, your mood. My therapist had me write down just like my mood sort of at every hour throughout the day. She's like, we need data for next week. I'm like, okay, I can get behind that.
Wow.
Just analyze it. Yeah.
Yeah. That's like interesting to like try to like understand a day-to-day or a moment-to-moment like change, or just journaling in that way.
Yeah. And you notice patterns, like we're as scientists, we are people who notice patterns, and you sort of write down, every time I exercise, I notice that, I kind of feel better throughout the day. And it's like, okay, that's something I can do to improve my mental health.
Yeah.
You notice those things, you can, create a lifestyle that works for you.
Yeah. Yeah. Like I've been like actually thinking a lot about kind of what happiness and productivity, like kind of how those two things go like hand in hand. And I saw a podcast with Cal Newport and Lex Friedman, and like I think Cal Newport says something about how like it's really important to value relationships, and that and it just kind of made me think that like sometimes I get this idea that there's geniuses and like they're always alone and like they accomplish something very grand, but like Cal presents a scenario where like there's events in life that you can't prevent, and like who's gonna be there for you, and like how do you maintain your own mental state in those times, and like it just kind of opened my mind to how important being like happy and prioritizing a life beyond your work can be. So I definitely agree that like it's really important to take care of all aspects of one's life, especially mental health, for long-term productivity and to be like a stable, sustainable person.
Yeah, I didn't even talk or think about it all, just how important relationships are. And like if my lifetime as a physicist looked like doing it by myself, I wouldn't do it. the really beautiful thing is having these people that are like going through the same things alongside you, and you see them like working through problems, and you see them with their trials and tribulations, and you have support from them as well when things get hard. And yeah, the physics community is just such a, I mean, scientists in general, I think, are just such, usually like open and humble people, just like learning and supporting each other and talking about science. And that's so important just for, I found even in this program where there's like 20 of us sort of all around the world, we still have Zoom calls to just like hang out at night and just, I've never met these people in person, but just to hang out with like my friends in the program and support each other with our academics and just with our personal lives too. It would be, not nearly as much fun without the people around us.
I think it's it sounds really useful that you have such a community that can keep you grounded.
Yeah, and people like flock towards the community. I mean, just in general, people flock towards community, and even like making a physics Instagram, I suddenly just like found all these people. I'm like, oh, whoa, there's like a community here. And, it's like seeing on the daily so many women in STEM too. I was like, wow, this is so inspiring. There are a lot of spheres in which I don't get to see that. Mm-hmm. Can't undervalue that.
Yeah. I was wondering if like you were to meet an undergraduate student and she were to want to pursue physics, what kind of advice would you give to her if she wanted to follow your path?
Yeah, so undergrad is like a time where you're really trying to figure out like what direction you want to take. And if that's leaning in the direction of physics, I would definitely say get involved in research. Don't think that you have to know any more than you do to get involved with research, because even if you're like helping prepare stuff in a lab or something, you're in a lab and you're learning about the experiment and you're talking to people, and you wouldn't learn any of that stuff from your classes anyways. So just like go learn it in a lab. The coursework gives you a solid foundation, but yeah, research is where you really learn to like what working on problems is like on the day-to-day, and like what experiments look like. It's a little harder to get involved in like theory research early on in undergrad, but finding out about experiments can be super illuminating in just what a research life is like. And I guess with regards to learning and course material, it's also, even still, like I'm learning how I best learn, but also applying, the scientific process also to your process of like studying. I think in undergrad, I like wasted time on studying techniques that didn't really work for me. Like I thought reading textbooks was like fun and easy. And so I would prepare for midterms by just like spending a week reading the textbook. And then I didn't know how to do any of the problems on the midterm because I had just like spent all that time reading the textbook. And, I really didn't internalize until recently that you just can't learn physics, especially these like problems and courses and stuff, any other way but by doing them. Sort of like if I wanted to learn how to drive a manual car, like I could read all the books in the world on it, but like I'm still gonna fail a few times when I get in front of the wheel, probably a lot. And it's only really by driving it that you figure out how to do it. Like that is literally the only way to see where like the gaps in your knowledge are, like see where your intuition's wrong, see where like the textbook didn't give you the right idea. And so the active, just like doing problems part, though it's painful because it involves just like a lot of failing and not knowing what to do. It's really, where you learn. We really only learn when we make mistakes. how would you like learn if you already know how to do it?
Right.
So that
Yeah. Like I've been like trying to do like a particular problem for like a couple of days now, and I haven't been able to solve it. And like, how would you approach that?
Yeah, I would definitely, I mean, in my situation right now, I would just like phone a friend or like message a friend on the internet, like, hey, have you looked at this problem? That's why I always did problem sets with my peers, like in undergrad. And I got really scared when I thought I wouldn't be able to do them with people this year, because I was like, I don't know how to do that. Like, what happens when I need help? And so just doing them, you learn so much by doing problems with other people. But if you're not in like a cohort or some situation where you can get a group together to work on something, I just like Google the hell out of things, you know, like somehow you can, or sometimes you can find people talking about your exact problem or even like the step you're stuck on. I Google so many things. Like I probably Google at least 50 things a day.
Yeah. Wow.
Even when I'm using Mathematica and stuff, I'll just random things like syntax. I'll be like, oh, like this is a function, but I don't know how to use it. Google. Like, I don't even know what the function is for this. Google. Just problems, you know. I don't know how to do this one thing with a matrix. Google. And usually I think you can find help that way.
Yeah.
And like Stack Exchange, there's just so much. Someone's run into the same problem before, probably.
Yeah.
And has probably asked about it on the internet. So it's just, yeah, awesome how much stuff is out there. Then also in textbooks and stuff, in theory, you should sort of have what you need to know to do the problems in the text. And so sometimes it just involves going back and like looking for something you missed or like a specific part that's relevant for the problem. Or maybe they just don't say anything about it in the text. You need to go to Google. But yeah, sort of asking other people, going to Google, reading the text, and then just letting it marinate in your brain for a while. Sometimes gets you to the end of problems. And I find with learning new things, it always helps me to hear it in multiple different ways. Because there's the way the textbook explains it, but then there's also the way that someone on YouTube explains it, or there's the way that, you know, somebody on their blog explains it. And it can just totally change your perspective of something when maybe from a textbook, you're learning it in this very like definitional way with these equations. And then if you watch a YouTube video, you just sort of get the big picture and you sort of get how it relates to other things. And then if you read another post online, you'll sort of see that, oh, the YouTube video missed this, or like it also has this whole level of understanding I didn't get. And that's something I also didn't sort of realize the power of in undergrad is like look up YouTube videos. There's so many on like everything. And, you know, somebody's put time into thinking about the best way to convey that information. And it can be just like so much more helpful than a textbook sometimes.
Yeah, I definitely agree. YouTube is just a really great resource, and I really think it's gonna change the way people learn from like now on. Or like it's been changing it too. So I love YouTube. YouTube rocks.
Yeah. When you think about the fact that like 50 years ago, nobody had Mathematica or Zoom or YouTube, it's like it makes everything so much more impressive that people did in like the early 1900s.
Oh yeah.
Like, wow, you really write this all out on a notebook. Yeah, when you think about how the potential to like accelerate science, that's really cool. Just, you know, we need all these computers and stuff to run like particle accelerators. So it's given birth to like so many new things that we can do. Anyways, the last thing I wanted to say is try to guess what's on your exams, because I think nothing on an exam should come as a surprise. instructors usually, this is again my like horrible technique of just reading a textbook for trying to prepare for exams. It's like I missed the fact that there was like this one type of problem we kept doing over and over that I still didn't know how to do. Like I could have very easily guessed like, oh, they've been stressing it a lot. That's one of the main points of the class. That's what they're going to test me on. Like the exams aren't meant to be edge cases or anything ever. They're sort of meant to test you on general concepts. And it's really easy to get so stuck in the weeds and like different problems and stuff that you miss the really like overall takeaways from class. Sometimes it's hard if a professor doesn't make that explicit. It's hard to get like, okay, what is this class about? Like, what are we studying? What are the main things I'm supposed to learn from this? What are like the main things I should come out of this class being able to compute? And so stepping back from that and like looking at the big picture and like the core like underlying philosophy of the subject you're studying, I think is very helpful and will let you, you should generally have like a good idea of the like types of things that are on exams to try to guess.
Yeah. Would you say maybe getting a practice exam online, like have you tried that out and maybe it helped you too, or just out of curiosity, I guess?
I remember in undergrad, a lot of our professors would give us practice exams like before the actual exam. And yeah, those are always helpful. But then of course, they're not going to ask you all the same things that are on the practice exam usually. So it's the same type of thing with like seeing things in as many different forms as possible. Like seeing other exams sort of shows you from a different perspective, like what's important in the class. And yeah, I think that would definitely be helpful. The least helpful thing you could do is focus on like the little specifics of calculations and stuff like that.
I definitely feel like I definitely feel like that would help me out when I begin my undergrad eventually. And for all the listeners who listen to this as well. I just wanted to thank you so much for your time. I'm actually out of questions.
Yeah, thanks for giving me the opportunity to share tips and stuff.
Yeah. No problem. And have a good day.
All right. Yeah, have a wonderful night.